Hi everyone! This time I will try something in 3D. It will be quite a simple thing, namely creating a tunnel from a texture, but even something as basic as that can sometimes be useful. And who knows, maybe I'll like it and next time I'll make something more sophisticated. So let's get started. Okay, so I talked about a texture, but this time it will be a part of the effect, not part of the scene. So we'll create a simple color rect and perform the usual setup. Right click and create new scene. Let's call it tunnel. Okay, and right click add child node color rect, and I'll do the usual setup as I said, change the size to 600 by 400 and add a new shader material, click and new shader, tunnel GD shader, canvas item, but I'll put it to the folder shaders and create and click to open in the editor. Alright, so as usual, let's get rid of everything that won't be needed. Right here, open vertex function, delete, and light function, delete. Very well. So I'll start with the usual translation of the coordinates origin to the center. Move it to the center and setting the correct aspect ratio. Yeah, sure. First, define the resolution. Uniform vec2 resolution. That would be the same as the resolution of our color rect. 600 by 400. And now in the fragment function, vec2 UV is UV minus 0.5, moving the origin from here to the center, and the aspect ratio UVX would be multiplied by resolution X divided by the resolution Y. Very well. So as I mentioned, we will transform the texture into a tunnel, but first we need to obtain the texture from somewhere. Instead of the usual noise texture, this time I'll use a texture from the material that was a part of the asteroid model from my space shooter game. But first, let's create a uniform parameter. Uniform sample 2D, tunnel texture, and let's set it to repeat enable because the tunnel would be indefinitely long. So we need the texture to cover it just indefinitely, of course. Okay, it should show up here in shader parameters, and I will add this texture over there. We can see it right here. Very well. So we can see how this texture would look in a normal display. I'll add these lines to the end of the fragment function. Vec4 pixel, let's read the current pixel from the texture using the function texture and tunnel texture, UV coordinates, and assign the result to the color. Pixel, yeah, sure, pixel, just pixel. Okay, wait for it. Yeah, here it is. Here it is, and it is transformed using our aspect ratio recalculation. So it's basically this square, and then it's repeated to the right. Very well. To transform a 2D texture into a 3D tunnel, we will need to perform several operations and transformations. For start, we can imagine that a camera is positioned in front of this 2D object, emitting rays for each pixel to determine at what distance these rays intersect with the tunnel wall. Such an array can be described as a three-dimensional vector whose first two components are the coordinates of the pixel, and the third one would be equal to 1, which corresponds to the direction from the camera into the tunnel. Let's define it here. Okay, so vec3, let's call it array direction, would be vec3. That is composed of the UV coordinates of the current pixel. This is vector 2, and the third one is, as I said, 1, the direction at the z-axis into the image. You know what I mean. Alright, for further calculations, we will need to know how large the tunnel actually is. We'll add a new uniform parameter and name it tunnel radius. Uniform float. Sorry, tunnel radius with some int range, and the initial value would be 1. The int range, let's make it from 0.1 to 4, for instance, and this step. Let's continue with the code. We know the direction of the ray, but we don't know its length from the camera to the tunnel wall. We will calculate the length using this simple formula. Right here, length is just a number, so it will be float ray length would be tunnel radius divided by the length function of the ray direction vector and only its xy coordinates, because we are interested in the distance of the UV coordinates from the center, which is 0, 0. So the length is exactly this. As we know from this previous line, ray direction xy corresponds to the vector UV, this one. Which are the coordinates of the pixel in the projection plane? So, as I just said, the closer this pixel is to the origin, to the center, the farther it appears when looking at the tunnel, so the ray length would be longer. This is logical because dividing by a smaller number gives a larger result. Now that we know the distance and direction, we can calculate the point of intersection. Vector 3 intersection would be simply direction multiplied by the length. We are just multiplying vector 3 by a float, which is a shortcut for multiplying every component of this vector 3 by the same number. Alright, now we will convert this point into polar coordinates because we want to display the tunnel, which is inside of a cylinder. The new point, denoted as P, will be a two-dimensional vector containing the angle in polar coordinates and the z-coordinate of the intersection point. Let's do it. Float theta is the angle in polar coordinates, and we get it using the atan function applied on the intersection y and divided intersection x. Actually, I could have used atan 2 and just a comma between them, but it is equivalent to this. Let's do it this way. And finally, as I said, vector 2p would be vector 2 applied on theta, the angle, and z-coordinate of the intersection. Here we go. And we will use this new vector in the texture function, this one, to rate the corresponding point of the texture. So instead of UV, let's change it to P. Okay, something is definitely going on here. We have the foundation of our tunnel. Of course, we see that it has certain flaws, which we'll gradually fix. I'll start by noting that the lighting should decrease with the distance from the camera, so we'll include the distance of the vector UV from the origin in our calculations. Let's do it here. float, let's call it dist, as distance is an internal function, so we cannot use this name, would be the length of the UV vector, and instead of just this, we need to multiply that by the distance. Okay, here we go. It's too dark now, so let's add a parameter for brightness. Uniform float brightness with a hint range and initial value. Let's make it 2 to enlighten the tunnel a little bit, and again from 0.1 to 0 to 4, and we will multiply the final color by brightness. Is it better? Yes, I would say so. Great. As the image clears up, we immediately notice another issue. The textures don't seamlessly connect here at the bottom and here at the top. So this is because polar coordinates have a periodicity in multiples of pi. So we need to incorporate pi into our algorithm. And it's very simple actually. All we have to do is to divide this theta angle by pi. Wait, and it's gone. Now it's seamlessly covered by the same texture. Perfect. This is finally starting to resemble a real tunnel. However, it's not ideal that the texture has stretched around the entire circumference. Let's add a parameter as a multiplier for texture repetition. Right here, uniform float, texture repeat with the hint range, and let's start at 4. So it would be repeated 4 times over. And since we don't want to repeat just fractions of the texture, let's make it like this from 1 to 10, and the step would be exactly 1. And we'll use it in the code. Let me copy and paste into this. We will multiply the angle by the repetition value. Okay, wait. Yeah, perfect. Now it looks exactly like I have shown at the beginning of the video. We are nearly finished. It might be useful to have the ability to control the level of the darkness at the end of the tunnel. Let's add one more parameter for that. Uniform float. Let's call it, for instance, tunnel fade. In range and start at 1.5, and it would be from 1 to 10 with this step. This is correct, and use it in the code. So the distance would be just power function of this length and exponent tunnel fade. Now it's done. The tunnel is finished, but it's not moving. So let's fix that right away. By the way, maybe there is the alpha channel, which is incorrect. I should have filtered it out. So instead of this, I will just change it to, wait a minute, yeah, vector 4, created from vector 3, pixel RGB, and multiply by brightness, and alpha is always 1. Now, yeah, it looks better, because the black is actually black, not a transparent color. And if I change the tunnel fade, it should gradually be darker or brighter. Let's put it back. Very well. So as I said, the animation, all we have to do is just to add the time value to the y-coordinate of the pi vector. Pi y increased by time. And it's moving. Here, you could definitely change the speed using another parameter that would be multiplied by the value of time. Adding this change can be seen as an optional exercise for you. Anyway, we're done. And if we wanted an elliptical tunnel instead of a circular one, we would just comment out the aspect ratio calculation, this line. Comment out, and it should become elliptic. Yes, here it is. Let's put it back. I hope you enjoyed creating the tunnel and you will achieve some great results with more interesting textures. Anyway, thanks for watching, and if you decide to click like, I'll appreciate it even more. Have a wonderful day and see you in the next video.